Steinhauer here. Welcome back. Continuing our discussion of light and how it's a wave and how that wave can be characterized with a wavelength. It turns out that our eyes are amazingly good at telling the differences between wavelengths of light that are very similar. In other words, we see those differences as colors. So here's a quick slide showing how this basically works. Again, there's a range of wavelengths that our eyes are sensitive to, and we pick up those different sensitivities, different wavelengths as colors. So on the short end of the spectrum, you probably heard Roy G. Biv. That actually goes from long to short. That is the order of the colors in the spectrum from long wavelength to short length. Roy G. Biv, R-O-Y, G, aqua's not in there, B-I-V, blue, indigo, violet. So at the long end of the spectrum is red, wavelengths in the 600 to 700 nanometer range. Orange is slightly bluer than that, slightly shorter wavelengths than that, and then yellow, green. And at the very blue end of the spectrum, you have blue, and it kind of goes purplish after that, although violet and indigo are very similar in colors, and violet's sort of just starting to drop off the page altogether. So that basically is it. Our eyes are sensitive to wavelengths of light that extend from about 400 nanometers to about 700 nanometers. There's two numbers here. You'll see nanometers are on the bottom, and there's this A with a circle over it above it. That's a unit called angstroms. And an angstrom, a nanometer is 10 to the minus 9 meters, and angstrom is 10 to the minus 10 meters. You'll see angstrom is a typical unit that astronomers like to use for light and wavelengths. Physicists are more comfortable with nanometers. We'll stick with nanometers here just because it builds on a unit that you also already know. So I'll be using nanometers almost exclusively in this class. But if you run into an angstrom every now and then, don't be alarmed. It's just a factor of 10 smaller than a nanometer. Okay, so our eyes see different wavelengths of light as different colors. Now, the portion of the electromagnetic spectrum, though, that is visible to us is a very, very small portion of all of the possible wavelengths that light can have. So the next slide is going through the entire, what we call electromagnetic spectrum. Really, light waves can come in any wavelength, from extremely short to extremely long. And what wavelength it specifically has, we give different names to it, but it all is physically fundamentally the same thing. It's an electromagnetic wave that's propagating through space at the speed of light. And all of these things have exactly the same process, exactly the same properties, with the exception of the energy and the wavelength. They're all just different forms of light, though. So here they are, from the very shortest to the very longest. We have gamma rays here at the very short end. What are we talking about here? Well, there's a wavelength scale here. If you can see it, wavelengths of 10 to the minus 12, 10 to the minus 11 meters, extremely short wavelengths. You're going to see here, there's lots of interesting things going on in this slide, but one of them is energy. This energy column here, you see the units, doesn't matter, it's electron volts. What I want you to notice is that at the short end, you have high energy, and at the long end, you have low energy. So the energy of an individual photon is governed by what its wavelength is, and it's inversely proportional to the wavelength. So the smaller the wavelength, the higher the energy. And so these gamma rays are the highest energy photons. When you see people talk about radiation, really that can refer to all light. But radiation that's harmful to us are these short wavelength, high energy photons. And if you're into superheroes, things like the Hulk get made when you exposed to too many gamma rays. What kinds of things make these? Well, on Earth, radioactive elements, plutonium, things like that. In cosmic sources, gamma ray bursts and things like that. Just longer wavelength than that, but still way shorter than visible, are the X-rays. And you're probably familiar with these from X-ray machines. These photons travel through flesh, skin, and muscle, but are absorbed by things like bone. And so in small doses, again, these are harmful photons. You should not stand in an X-ray machine for very long, but in small doses, they can provide some valuable imaging, diagnostic, medical information to doctors and things. You know, in the 10 to the minus 10 to 10 to the minus 9 to 10 to the minus 8 range in meters. Things cosmically that produce X-rays tend to be compact objects like black holes, and or at least accretion disks around black holes and neutron stars and things like that. Just shorter in wavelength than the visible is the ultraviolet part of the spectrum. You've probably heard of UV rays. That's what we're talking about, ultraviolet rays. The sun produces some ultraviolet rays on the long wavelength range of this ultraviolet region. And so these are more energetic than the visible photons that we can see. And so they can do more damage. And so when you put on sunblock, you are trying to limit the effect of particularly these UV rays, UVA and UVB, depending on which part of the spectrum you're in, that actually does come from the sun and can be damaging to us. So the sun's chromosphere high up can produce some of these ultraviolet photons. And you can see, here is the visible part of the spectrum, this little rainbow here. That is the shortest by far of all of these wavelength regimes. It's a very small range where our eyes are actually sensitive to. We'll talk about why that is as we move along, but that's it. The region that our eyes are sensitive to is just that. And things like light bulbs and the sun's photosphere are giving us those kinds of energy photons. Just longer than the sun, you get into a region called the infrared part of the spectrum. Again, these are longer wavelengths and lower energy photons than the visible part of the spectrum. And eventually you get long enough that you go out and you get into these very long wavelengths, radio waves. And microwaves kind of inhabit the intermediate range between infrared and radio, although different sources you'll see will define these slightly differently. It doesn't really matter. But there's no limit to how long a radio wavelength can be. The wavelength can be physical sized objects like baseballs and football fields, and even longer than that. These become difficult to detect as they become really large, because you kind of need a receiver that is larger than the wavelength of the wave you're trying to detect. But they do exist out there, even if we can't see them or even detect them. So that is the entire electromagnetic spectrum, from the shortest to the longest, and from the highest energy to the lowest energy. Okay, I mentioned that energy was inversely proportional to wavelength. Can we be more specific than that? Can we be quantitative about that? Of course we can. There's an equation for that. So here it is. Here you see it, energy inversely proportional to wavelength. You've got energy on this side of the equation, and you've got wavelength in the denominator on this side of the equation. So if you double the wavelength, you have cut the energy in half. That's sort of how I want you to think about these equations. How are they related to the variables involved? So this is the equation. It's pretty simple. E equals h times c over lambda. We already know what c and lambda are. C, of course, is the wavelength, and lambda is the wavelength of the light we're talking about. H is just another constant. It's particularly called Planck's constant, and it's got a really, really small value, like the smallest value you've ever seen in your entire life. 6.6 times 10 to the negative 34. That's hard to, I couldn't even draw that if I wanted to. I probably couldn't even write that many zeros across this page if I wanted to. That's a 6. It's a 0.33 zeros and then a 6. We're not going to worry much about what this constant is. I'm not going to use it much. You can look it up if you need it. It's got weird units too, kilograms times meters squared per second. I'm not going to try to interpret that for you. It doesn't really matter. We can use this though to calculate the energy of a photon, and we can use those units to figure out what the unit of energy has to be? Because we haven't really talked about energy. What is energy? Energy is the ability at some level to do some work. It is, you have a concept of what it is, but defining it is actually pretty difficult. But we can define its units fairly easily because the energy, units of energy will have units of H times C divided by lambda. So let's go ahead and do that exercise and figure out what the units of energy have to be. So again, this is what I'm going to use for units of energy equals the units of H, which are kilograms times meter squared per second, times the unit of C, which is meters per second, divided by the units of wavelength, which is just meters. So this is kind of confusing because we've got a fraction in the numerator. As always, we can just move the seconds down to the bottom, and we've got really a denominator in both of these things here. But these seconds can just drop down to the bottom. The meters are going to cancel out, some of them anyway. So this meter will cancel out this meter, and that's really all we need to do. The rest of them sort of follow along. We've got a kilograms on top. We've got a meter squared on top, and we've got 2 seconds on the bottom. So that gives us a second squared on the bottom. So the unit of energy is kilogram times meter squared per second squared. This is, you might recognize it, similar to the unit of force, right? A force was mass times acceleration, kilograms times meters per second squared. This is meters squared per second squared. So energy is somehow force times distance, which is another way to think about what energy is, right? Energy is how far you push something with a particular force. You can calculate energy or work in that particular way. Anyway, again, we don't want to be writing kilograms times meter squared per second squared all the time. So we have a nickname for this unit. 1 kilogram meter squared per second squared is equal to a joule. So, or just J. Usually we'll denote that with a capital J. So if I say joules of energy, I'm talking about kilogram meter squared per second squareds of energy, but it's a heck of a lot easier to say joules. So I'm certainly going to stick with joule. Okay, let's try this equation out for size. What is the energy of a 500 nanometer photon? Our formula is E equals H times C over lambda. We can just plug those numbers in. That's 6.6 times 10 to the negative 34. I'm actually, let me go back for a second, because this kilogram meter squared per second is pretty darn close to a joule, isn't it? In fact, sometimes you will write Planck's constant instead of kilograms meter squared per second as joules times seconds, right? And that makes it even easier because if you want to end up in joules, you don't have to do the conversion at the end or think about it. And if you use Planck's constant as joules times seconds, the joules will just pop out. So let's say instead of being kilograms meter squared per second, this is just joules times seconds. Okay, I'm going to multiply that by the speed of light, which is 3 times 10 to the 8 meters per second. And then we divide that by the wavelength of the light, which is 500 nanometers, or 500 times 10 to the minus 9 meters. Okay, so plug that in your calculator. I want to do a brief aside now on your calculators, how to use scientific notation, because I probably should have mentioned this earlier. Different calculators will do scientific notation in different ways, but if you bought a scientific calculator for this course, which you should have, I said it had to have an EXP button or an EE button. Your calculator probably also either has a caret button or a X to the Y button. And you can, if you want to, use these to do scientific notation. But I'm here to tell you, you're going to get into a lot less trouble, and it's going to be a lot easier if you use these buttons. These buttons mean times 10 to the. So in other words, if you plug into your calculator 6.6 EE or EXP, depending on what your calculator has, negative 34, that's going to tell it that that's a single number that is 6.6 times 10 to the negative 34. 6.6 EE negative 34 times 3 EE8 divided by 500 EE negative 9 is the simplest way to plug that into your calculator. You can get into trouble with the caret and the X and the Y, and I'll tell you why. This will work. You can type 6.6, you can put the times button, you can type 10, and you can do the exponent x to the y negative 34, and you'll get this number. First of all, it's way more buttons to press. But second of all, but it will work. You can get into trouble though, because if you're dividing by 500 times 10 to the minus 9, your calculator thinks that 500 and 10 to the minus 9 are two different numbers. And so if you say divided by 500 times 10 to the minus 9, it might divide by 500 and then take that whole thing and multiply it by 10 to the minus 9 instead of dividing it by 10 to the minus 9. You can get away with that by putting this whole thing in parentheses. But those even more characters to have to push in, and you have to remember it. If you use the EE and EXP button on your calculator, you don't have to worry about parentheses. It will know 500 EE negative 9 is a single number, and that you should divide all of this by that single number. So use your EXP and EE button, learn how your calculator works, and it's very important. So plug it into your calculator. What do you get? You get E is about 4 times 10 to the negative 19. Now, what are the units on this thing? We've got meters in the numerator and in the denominator. They cancel out. We've got seconds in the numerator here and a 1 over seconds in the numerator here. Those also cancel out. And we're left with the unit that we expect, which is just joules. Is this a lot of energy? The answer is no. It's a very, very small amount of energy. A very small amount of energy. In fact, how small is it? Well, a 60-watt light bulb gives off 60 joules every second. That's what a watt is. It's a joule per second. That is a lot of photons, right? Every one of them, this is a typical visible light photon, right? This is typical of the energy of the photon that's coming out of your light bulb. A 60-watt light bulb gives off 60 joules of energy in 1 second, or at least it consumes 60 joules of energy in 1 second. Each of those photons is only 10 to the minus 19 joules. You need 10 to the 19, 10 to the 20 of those photons every second will be streaming out of your light bulb. That's an incredible number of photons. But it's why your 60-watt light bulb can illuminate an entire room. Remember, those photons not only have to leave and bounce off of things, but then also they will be radiated in all directions and some of them have to reach your eye. Enough of them that you can tell that the object's there and even what color it is. We're talking about a lot of photons flying around in a typical room that's lit, even with a 60-watt light bulb. Okay, I've got one more question for you, and that's this one. I've already given you the answer a little bit, but let's see if you remember or understand how this formula works at least. How does increasing the wavelength of a photon affect its energy? If I make this get larger, how does that affect the energy of the photon? Will it increase the photon, decrease the photon? I'll make it stay the same. Okay, now that you've guessed or told the right answer, the answer, of course, has to be decreasing the wavelength or decreasing the energy, right? Energy is inversely proportional to wavelength. If I increase this number on the bottom of this equation, again, H and C are constant. They can't change. If I increase the wavelength, that has to mean I'm making the energy smaller. Okay, I'll stop there. We'll come back and talk next time about how matter is made up and how light interacts with matter. See you then.